Well, let's pretend we have a potential real-life situation here where we have a beam that's loaded with this load of bricks, and then we have this other weight hanging off the end. How about if we draw that as a distributed load like this, and with a point load, a force right over here. So let's go ahead and try to solve this one. So what we want to do is then model this as a triangle load on this side with a peak of 15 kilonewtons per meter. And then we want to want this side over here as a triangle load with a peak of 10 kilonewtons per meter. This trapezoidal area in here we'll model as two loads. In other words, this will be a rectangle load in this area and a triangle load here. And what we're looking for is we want to find the equivalent resultant force and specify its location on the beam measured from point A. So to find out the resultant force, basically we're looking for the sum, if you will, of the center of gravity of all this stuff plus that one. And that resultant, or that sum of all those things, will be the resultant force. So let's go ahead and draw in the resultant force right now. And this is really what we're looking for, the resultant force and the distance, x bar, that it is from point A. Alright, this point load we're going to say is 20 kilonewtons. Let's go ahead and then draw the 3 or the 4 loads. So we'll talk about this one, and this one will have a resultant force. Call this R1, and it'll be separated a distance x1 from that point A. This next area, we're going to call this the triangle part of it. This will be R2, and this will be x2. Then the rectangle part we'll call R3. I'll just extend this up here. This will be distance x3. And then the last part over here is this triangle area over here. And we'll call the centroid distance to that one, we'll call this R4. And this distance x4. Okay, I'm hoping that you see all of those distances and all of the resultants. Let's go ahead and then write down, or figure out, I guess, what those resultants and what those x's are. Okay, first of all, let's I think I can get rid of that now, and let's talk about the individual resultants. Okay, so R1, switch to black. R1 is going to be equal to, because this is a triangle load, it's going to be 1/2 BH. So that's 1/2, the base being 3. This is the base of that triangle. And the height is 15 kilonewtons. So 1/2, 3, 15. That's equal to 22.5. Now x1, because this is a triangle here, it's going to be the centroid of that will be out in here someplace, and that's the distance through which that resultant acts. It'll be 2/3 from that side, 1/3 from this side. So if we're looking from this distance here, it'd be 1/3 of 3. So x is equal to 1. R2. R2 is also a triangle load, so that's going to be 1/2 BH. Now again, the base is 3. Now here's something to just note. This height right here is 10. This is 15, so the triangle part of it is just that 5. So this would be 1/2 base times that height. So it'd be 1/2 3 times 5, and that's going to be equal to 7.5. x2 is also equal to 1, because that's just going to be 1/3 over from here, 1/3 of 3 over to there. Alright, how about R3? This is a rectangle load, so that's just going to be BH, which is 3 times 10, which is equal to 30. x3 is just going to be 1/2 of the 3, so that would be 1.5. And then R4. Again, another triangle load, so that's 1/2 BH, and the base is 3, and the height is going to be 10. that's 15. And x4 is going to start with this 3, and then 1/3 of that 3, so it would be 4. All right, I hope that we can see all of those. Let's find out what the total resultant force that we're looking for. So R, the big R resultant, is going to be equal to all of these individual distributed loads plus that 20. So it'll be 22.5 plus 7.5 plus 30 plus 15 plus 20. And that's going to be equal to 95.0 kilonewtons. Okay, that's our big resultant. Let's find out what the moment before is. The moment before, I think I can maybe zoom out here so I can see all that. The moment before, so these are all the before kind of things. Moment before is going to be the effect on A, the moment about A, before we replace it with this large resultant. So let's see what the moment about A is. In the positive direction, that'll be R1 times X1. That's obviously going in this direction. Then R2 will be going in this direction, R3, R4, and then the 20 kilonewtons will be going also in that direction. So I'm just going ahead and write all those things down. It'll be R1 times X1 minus R2 times X2 minus R3 times X3 minus R4 times X4 minus that 20 times 6. Alright, with that, I'm going to go ahead and then put all the numbers in, and then we can catch up here in just a second. Okay, so I've computed the moment before by putting all those numbers in, and we can see that it is negative 210 kilonewtons per meter. Alright, let's find out what our effect is afterward. And the after effect is replacing all of this stuff with one resultant times that x bar. So let me go ahead and zoom up just a little bit here. And I'll say that the after the moment about A is going to be equal to the same, which is negative 210, and that's going to be equal to the resultant times x bar. And I can divide that out. I can see that x bar is equal to 210 over 95, which is equal to 2.210. Alright, so what we've done then is replaced all of those loads with one load, which is the resultant load at that distance. I want to do one more with you with distributed loads, and this time instead of adding a point load, we're going to add a couple. So this force here is going to be the same as that force, and let's put some numbers in there. I'm going to say that this is going to be 500 newtons, 500 newtons, and this one is 500 newtons, and this distance that it's separated will be 2 meters. Okay, again, what we're trying to do is replace this distributed load with a resultant force and specify its location from point A. So I'm going to go ahead and draw the resultant force. This is again the unknown. This is what we're looking for. This is the resultant force, and the x bar is going to be the distance from point A. We can model this. This is a rectangular load. This is a oh, wait a minute, that is a trapezoidal load because it ends at 200, which means I'm going to have to model this as a triangle this way and then a rectangle this way. So I'll go ahead and draw all those pictures together, and we can see what it looks like. Okay, so what I've done is filled in the R's and the X's and the total resultant. So this would be our R1 for this rectangle load. Its distance x1 is equal to 1. Again, this is a rectangle load, so that's just BH. R2, this being a triangle load, it's going to be 1/2 BH. and the total distance, or the total sub-resultant, is 900. R3, back to a rectangle load, B times H, and so that is 600. The X3 is going to be 2 to this point, and then half of 3 goes out to here, so that would be 3.5. Then the total resultant. Let's add all of the forces that we see. Got negative 1600, negative 900, negative 600, and that's in the J direction. Now I'll need to add this couple in here, so I got positive 500 in the I, negative 500 in the I. Obviously they cancel out from some of the forces in the X direction, and here we have our resultant. Now what we want to do is find out what let's find out what the moment about A is in the before condition, and then we'll figure out what X bar needs to be. Okay, then what we've done is computed the moment before. The moment before is going to be this 1600 times x1 minus this 900 times x2 minus this R3, that would be 600 times x3, and we also have this couple, and this is also going in this direction, so it would be 500 times 2, and that's what I've computed, so that would be negative 7400, and that's going to be equivalent to the moment afterward, which is the resultant force times x bar. And so that I have right here, the resultant force was equal to 3100, and you can compute x bar is equal to 2.39. So that gives you a little introduction here about how to find equivalent systems using distributed forces.